last time we talked about law of sines. Today we're going to look at law of cosines. Law of cosines. Okay, if you remember, we started off the last lecture with 4 ways to solve an oblique triangle, right? And we looked at 2 of the ways last time. I think it was the angle, side, and the what? Side, angle, okay? Today we're going to look at the other 2 cases. We're going to look at the side case and the side, angle, side case, okay? So for these 2 cases, we're going to use the law of cosines. The law of cosines have 2 forms. The first is the standard form. And for this, we will use to solve for a side. Like a squared will be b squared plus c squared minus 2bc cosine a. b squared equals a squared plus c squared minus 2ac cosine b. And c squared equals a squared plus b squared minus 2ab cosine c. Now this is the standard form. This is if we know 2 of the sides and we know an angle, okay? We have an alternative form. This alternative form gives us a means for finding the angles. Cosine A equals b squared plus c squared minus a squared all over 2bc. Cosine B equals a squared plus c squared minus b squared all over 2ac. And cosine C is a squared plus b squared minus c squared all over 2ab. Okay? So, we use the alternative form when we're looking for an angle. We use the standard form when we're looking for a length of one of the sides. Now, we are going to use law of cosines to help us find other information about these angles, but once we find information, we may have to revert back to the law of sines. Okay? We can use either or. So, as a note, when we use the law of cosines to help us find the other components of this triangle, it is going to be best to find the largest angle first. Okay? It's best to find the largest angle first because knowing the cosine of an angle you can determine whether the angle is acute or obtuse. Okay? And we know that acute angles range from what? 0 to 90. So, for cosine is greater than 0 for angles ranging from 0 to 90 degrees, which means what? The acute situation. And if cosine is less than 0, because what? A triangle has how many degrees? 180, which means we're either going to deal with quadrant 1 or what? Quadrant 2, right? So quadrant 1 goes from 0 to 90. So that means we have an acute angle, and there cosine is greater than 0, right? Here cosine is less than 0, in the second quadrant, and that's for all angles between 90 and 180 degrees. Obtuse. Okay? So, why is it helpful, or why do we want to find the largest angle first? Okay? It's just because we can know the cosine of that biggest angle. Now, let's talk about triangles for a minute. The angle and the side opposite that angle are related, right? Your largest angle will also be your what? Longest side. Okay? Your smallest angle will be your what? Smallest side. So we can figure out which angle to find first. Okay? We can figure out which angle to find first. Let's look at an example. Suppose we have this triangle where this is angle A, angle B, angle C, and we're given that the side opposite angle A is C is 9, the side opposite angle A is 8, and the side angle B is 3. So we're in this side situation, okay? Now, it told us that we need to find what? The largest angle first, which means we need to find what first? C. Remember, the longest side corresponds to what? The largest angle. So let us find C first. We have that cosine C is what? A squared plus B squared minus what? C squared all over 2 times A times B. Okay? And if we do all this, we get that cosine C has an approximate value of negative 1.666, which means this is what? An obtuse angle. We're in the second quadrant. Okay? Now, if we do that inverse cosine on our calculator, see what do you get? See, do you get the first quadrant or the second quadrant angle? What do you get? I did my notes way last week and I don't remember. Putting it in there? Yeah, because it's negative, huh? Are we getting 99 out of there? I'm thinking we are because I didn't make a note.
Give me an error. Wait, how did you get cosine? I got bigger.
You got a bigger number.
You get, I don't know how to get it.
Let me see. I could have very well done something wrong here. You got what? Are we in degree mode?
And mine's in degree mode.
Gosh, what are we getting? Negative what? Negative 96. That shouldn't happen. Let me see that little bitty calculator you have right there.
I think that's supposed to be 0.166.
Is it? I was about to check this. 64 plus 9 minus 81 equals divided by 48. Yep. Okay, that's the problem. I'm glad I had you check that. What was that? Negative what? Did you erase it already?
Oh, yeah.
No, for the cosine. I mean, for the cosine of that angle. Let's see. 64 plus 9 minus 81 divided by 48 is negative 0. I should have 0.166. And what do you get there? Of all days, I didn't bring my calculator either. What do you get there when you do inverse cosine?
99 I got 99.55.
Okay, and it could be the way your calculator is calibrated. Sometimes we kind of want to round to the hundredths place, but it depends on your calculator and how they round this number
Are you gonna be kind of
I'm going to be lenient there.
lenient there?
I would take 99.5. I would. I'll be lenient.
Okay. You got 80.4.
80.4. We won't take that one now. Let's see.
Okay. Well, how'd you do it? I must put something wrong.
I think with yours you have to put negative 0.1666 and then the second function and then cosine. Nope. You got to do it the other way.
Right. Do it opposite.
Yeah. Negative cosine, negative 0.1666. You probably just entered something in wrong. Okay, y'all. But we know one of the angles now. And here we had to find how many angles? All three of them. So knowing one angle and all sides, now we can go back to what? Law of sines if we want to, right? We can go back to law. Well, you can go back and do the alternative form, but law of sines is easier, is it not? So let's go back to the law of sines. Now, knowing that this angle is what? Obtuse. The other two angles are going to have to be what? Acute, right? There is a property that says a triangle has at most one obtuse angle, right? So the other ones are going to have to be where? Somewhere in that first quadrant. So now let's use the law of sines. Sine C over little c equals sine A over little a, right? So sine A, if we solve for that, we can multiply both sides by little a and put it in here. Little a is 8. We have sine of what? 99.59 degrees all over little c, which is 9. So sine A is approximately 0.876. 0.876, which means A, if I put in what? Inverse sine. Are you checking my work there? Sure. You have two calculators over there. I think you're more than able to check it. See if what I'm getting is correct. All right. I'm correct there. So now, I may not can work yours. Let's see. You mind if I get chalk on it today? I should be able to work this one. Is this like my TI-83? Is it similar?
Yeah, pretty much.
Okay. He's going to let me use the calculator today, y'all. The titanium now, y'all. TI-89 titanium. This costs some mega money. Maybe I should get the other one. Okay. All right. So, I have my angle A and my angle C. I need to find what now? B. And that's just a matter of doing 180 minus what? 99.59 minus 61.22. So this B is approximately 19.19 degrees. So we can see that this law of cosines is a little bit easier, isn't it, to work with?
Now, why are you going to use the law of cosines and then go back and use the law of sines?
Well,
You found the first angle using the law of cosines.
you can find the other angles using these forms too, but the law of sines is easier to work with. You can use the law of cosines, don't get me wrong, you can, if you want to, and you should get the same angle.
It's just easier to do it that way?
Because you can easily remember sine C over C is sine A over A. Because with this law of cosine situation, we're not going to have that case where you have two triangles and all that stuff. So you can go back to the law of sines. Question in the back.
We're going to have all the formulas and forms and stuff on.
I don't know yet. Let me think about it. I think you want me to think about it, though, wouldn't you? I'll think about it and I'll let you know.
You take bribes?
No, because I am a Christian woman.
Christian women take bribes? Yeah. Christian women need money too.
I need money, but I'm not going to take bribes.
How about time gestures?
We have another question in the back.
Yeah. I'm still at a loss how you got that first one.
This?
Calculator. Like, now that you have a calculator, can you explain how you do it?
Yeah. What kind of calculator do you have back there?
I just have the TI 36.
Do you have to put in the inverse cosine first?
I think what me and you done is, because I got the same answer she did. Because what I did is I pushed the divide button, divided by 2 times 8 times 3.
And you didn't put parentheses around it.
That's what we did.
Yeah.
What's the difference?
Well,
48, like, I divided -8 by 4. Like, if you took 8 squared plus 3 squared minus 9 squared, you get -8. And I just took -8 divided by 48.
and you didn't get negative 0.166?
Oh, I did this time.
It's okay. Hey, we all have problems punching in buttons. Because I had some problems even with this one, which I'm glad I had you check my work. Because somebody would have been looking at this DVD and they would be like, that is not what that's supposed to be. So, I welcome you correcting my errors. I really do. All right, so we looked at the side. Let's look at a side angle side situation. Okay? Not so bad as the law of sines, is it? Suppose we're given that B is 75 degrees and what? 20 minutes. I know y'all love this minutes and degrees stuff.
It's not hard, it's just extra.
It is extra.
I like to put that in there.
A is 6.2 and C is 9.5. Now, I probably need to go ahead and change this to degrees, right? And how do you do that? Okay, so that's 75 point what? 3 with a little bar degrees. And we'll go ahead, and since we're going to do the 2 decimals, we'll just say 33, okay? Approximations are good here. And on a test or whatever, I would not care if you didn't convert back, okay? But, you know, as in practice problems, they're going to have these types, and you need to know how to do them, okay? So, I know little a and little c. I can use law of cosines over there to find what? Little b, can I not? B squared is, by that formula, a squared plus c squared plus c squared minus 2 times a times c times cosine 75.33 degrees. And hopefully we can figure all that out. Take the square root. 9.94. All right, he's checking me, y'all. That's good. So that's B. So I have all 3 of my sides and what? 1 angle. And what do I need to do here? I can go back to the law of sines, can I not? I can, or if I want to do the law of cosines, I can do the law of cosines, but the law of sines is easier to remember. Sine big B over little b is sine big A over little a. So if I want to find angle A, I multiply both sides by little a. So what do I have? A, 6.2 times sine 75.33 degrees all over what? B, which is 9.94. So I get, and I didn't get what sine A was, but I went ahead and did inverse sine, and I got 37.12 degrees. You got what?
37.1.
Okay. In rounded,
So given any triangle, you can use, with any of the sides or angles, you can either use the law of sines or the law of cosines, and you'll get the same answers. This is just two ways of working the same problem.
No, it depends on what you're given.
Okay, some of what you're given.
Right. It depends on what you're given, what you use for. If we're given 3 sides or 2 sides and an included angle, then we can use the law of cosines first to start off. Then in the problem, we can revert back to law of sines. The other situations, we need to use law of sines.
What if I came up with 37.08?
Ooh, that's way off. Is that what you did by doing .33?
Was it?
Did you do .33? Because what I did when I did this on my calculator, I just copied and pasted the value, so I had a lot of 3s. And depending on the amount of 3s you have, I have to see if I would be that lenient. So you may want to. Yeah, that's true. That's true. We'll have to see, but just know I will be lenient on that, with these angles. For that, you may get a point taken off versus getting full credit, because it's kind of off.
Hey, it is approximate.
It's approximate, you're right. How do I find angle C? 180 minus what? These 2 degrees. 67.55. And like I said, on my calculator, I probably had all the 3s that could go in the calculator. And I have a larger calculator. You may not can get that same approximation on something that's not graphing like these that we have here. So, yes, I'm going to be lenient. I'll be lenient. So those are 2 situations. Law of cosines is a little bit, a little bit easier. If you're given the formulas, he says. We'll see. In fact, I'm kind of thinking of some things I'm going to let you do, but I'm not going to say it right now. No, I'll tell you later. Okay. Heron's area formula. You remember in the last class we had formulas for the area of an oblique triangle? Do you remember that? Well, we can now find the area using Heron's formula. It says, given any triangle with sides of lengths A, B, and C, the area of the triangle is given by the square root of S times S minus A times S minus B times S minus C, where S is A plus B plus C, all divided by 2. If you remember, in the finding area of an oblique triangle in the last class, we had an angle, and we had 2 sides, right? Here we have what? 3 sides. We don't need an angle here. So, depending upon what you're given would depend upon the formula that you use for what? For this triangle. So, and they will give you all 3 sides. So just as a brief example, find the area when we're given sides 12, 15, and what? 9. So the first thing you may want to do is find what? S. So we have 12 plus 15 plus 9 divided by 2, which is what? 18. Okay? Then to find the area, 18 times 18 minus 12 times 18 minus 15 times 18 minus 9. And what do we get? 54. Okay? So as I said before, y'all, the law of cosines, it is not as involved as the law of sines. You don't have all those cases. Okay? You don't have all those cases. Yes.
I went back and added on that one where I said I got.
Some more threes?
Well, I added 4. I didn't add that. I just put once you go 3, I added 4 at the end of it.
Wait. What are you talking about?
On that one right there, the other problem. 37.12.
Uh-huh.
I came up with, when I added that 4, I came up with 111, so it's a lot closer.
Okay. Any question about the law of sines? I mean, cosines. Law of cosines. Okay. We're now going to move and we're going to talk about vectors in the plane, okay? And we do want to take our time with this, and this is a pretty long topic that, of course, we will not finish today. As a matter of fact, we're kind of getting ahead of schedule a little bit because this is supposed to come in the next class, but it's so long to where we will not be able to finish in one class. So we're going to go ahead and start it today, and we'll finish it up in the next class, okay? So, and we try to do things and keep on schedule. So this will keep us right on schedule instead of getting behind. Vectors in the plane. And I must say, how many engineers we got in here? How many people want to be engineers? Okay. You need to know about vectors. Physics, vectors, almost synonymous. Okay? Once you get to calculus 3, how many of us have to go to calculus 3? Vectors. As a matter of fact, it's called vector calculus, vector analysis. So you need this foundation of vectors. And to my understanding, as far as Math 100 goes, you don't see it there. You don't see it in 112. This is where you're really introduced to it. So we do want to take our time and get you familiar with this idea of a vector. He says yes. I don't think it's so hard. In fact, I like vectors. I know, and I have a minor in physics, so I like physics too.
Probably explains why it's not difficult for you.
Well, maybe so. But I have a minor in physics. And to tell you the truth, I did better in my physics courses in college than I did in my math course. I made all A's in my physics, but I didn't make all A's in my math.
Should have made it in physics.
They tried to get me to change.
Why didn't you?
Because I was almost done with my math degree. And physics, it's okay. I like the math part of physics, though. Some physics I don't like, so. Anyway, physics, going into calculus 3, and if you have to take calculus-based physics, you need to know this. You need to get the foundation here so you won't be lost. So, vectors in the plane. Okay, quantities like force and velocity. They involve magnitude, which means some constant, as well as direction. Okay? So not only do we, we can say that, and here if we talk about the speed limit, 55 miles per hour. Okay? Really, that's not speed. Well, it is speed, but it's not speed. It's really, when you think about it, in physics, it's velocity. It's velocity. And you don't say, and I know it seems foreign, for the police officer to say, well, what is your velocity? They say your speed. But really, when we talk about miles per hour, we are talking about velocity. And it has a direction associated with it. Okay? So, how do we come up with these quantities like force and the quantities like velocity and acceleration? Where does this direction part come from? Where does it come from? Well, if we use what's called a directed line segment to represent such a quantity. A directed line segment. So, what is a directed line segment? Suppose I have this line. I start my initial point at P, and I draw a line out here somewhere in this plane to the point Q. Now that is a line segment, but it's not directed line segment until I put this arrow here. Putting this arrow here tells me that I start at P and I go to Q. So what this is we have a line segment PQ with an arrow above it. That's a little half arrow. Okay?
What is the half arrow?
It's just notation. The book might use a whole arrow, but, you know, we use half arrows here to denote that. Doesn't matter. Doesn't matter to me at all. Okay, so the directed line segment, which I'm going to abbreviate DLS, PQ has initial point P and terminal point Q. Its magnitude or length. Magnitude and length are synonymous here. Is denoted by this notation. We put double bars around this directed line segment PQ. This means that I'm going to find the length or the magnitude, and this can be found by the distance formula.
What's the little thing again?
What? These vertical lines. They're just called lines, vertical lines. Two vertical lines on either side. Doesn't have a special name. Not to my knowledge. I take that back. There is another way. You can say the norm of, and that means length. But we'll just refer to it as length. So another way we can say the length or magnitude is the norm. But you probably won't hear that until you get on up higher in physics.
What does it say for big U's is and what?
Can be.
Oh,
Can be.
trying to read one word, like, what's that?
I know it. I didn't put enough space between my letters.
So,
Okay. Two directed line segments that have the same magnitude and direction are equivalent. Okay? They are equivalent. So, two directed line segments having the same magnitude and direction are equivalent. The set of all directed line segments that are equivalent to the line segment PQ is a vector V in the plane. Written as V equals PQ. So we said that two directed line segments having the same magnitude and direction are equivalent. But the set of all directed line segments in the plane that are equivalent to this directed line segment forms a vector, okay, and we call that vector V. Now, if you notice, in most textbooks, the vector V or all vectors will be bold-faced, okay? They're going to be bold-faced. But because we're up here on the blackboard and you're going to be sitting there writing your notes, we denote vectors with that little arrow, okay? But in all textbooks, for the most part, they are bold-faced letters, okay? But we draw the arrows. Okay, so this kind of explains what a vector is. Let's talk about some properties of vectors. Let's look at the component form of a vector. The component form of a vector with initial point P, and let's give that point P some coordinates, P1 and P2, right? Our same initial point here, and terminal point Q, which is Q1, Q2. This is like our terminal point. Where our arrow ends, that's our terminal point, okay? Then the component form of this directed line segment PQ will be, and we draw the little backward equal signs here, you know, to denote that this is in component form. Q1 minus P1 is the first component. Q2 minus P2 is the second component. This becomes our V1 and V2, which make up our vector V. Now let's talk about what they're doing here, the component form. We have a point just out there in space, right? It could be anywhere. When we get the component form of this vector, what happens is we push the initial point to the origin. Okay? That's what happens. We push the initial point to the origin. For example, let me make up an example here of this component form to better explain what's going on. Suppose we have a directed line segment in the plane here. Let's say this is my initial point and this is my terminal point. That's my vector. I call this my P and this my Q. Okay? This is the point what? 1, 2, right? And this is the point what? 1, 2, 3. Is it 3? 1, 2, 3, 4? Okay, suppose these are my points. Well, this is my directed line segment PQ, but I want the component form, which means I want to take this whole line here, move it down to where my initial point is the origin. Okay? And it's going to be helpful for us to work with component form vectors when we start adding and subtracting. So, if I find my vector V, then what I need to do is do what? This is my P1, P2, Q1, Q2. So I do Q1 minus P1 and Q2 minus P2. So my component form of my vector is 2, what? 2. So what that means now is that my P has moved here, and now I'm at the point 2, 2. This is my same vector, but what has happened? I have moved it where my initial point is now at the origin 0, 0. That's all component form is. I'm moving that vector to where my initial point is at the origin. And it's going to help me when I do operations if I have the component form of that vector. Does that make sense now? And I realize this is different. It's different. It's different, huh?
I was saying, you understand that now? I was going to say, how do you manage this?
It's different. So we can get the component form, okay? Now we talked about the length or the magnitude of this vector. What is the formula for that? The magnitude or the length is given by. Now it depends. If we are given a vector that's not in component form, where we have the same P and Q here, then it's going to be the distance formula. The distance between those 2 points is going to be Q1 minus P1 squared plus Q2 minus P2 squared, which is the square root of V1 squared plus V2 squared, if we're in what? Component form. So this is if we're not in component form, we have a point P and Q, and this is the formula for if we are in component form. Because if we're in component form, our initial point is the point what? 0, 0, the origin. Okay? Now, as a note, if the magnitude of this vector is 1, then this is a unit vector. If the magnitude is 1, then we have a unit vector. Okay? Yes?
I still don't know why we're putting in 2 lines or everything.
All that means is that we're finding the length.
Oh.
That's the short notation for finding the length or the magnitude. That's why.
I'm just lost. I mean, I understand how you got that. I don't know.
Right now, the only thing we've really done is put this in component form. We're really just throwing a lot of information at you that you will need to know, but we probably won't get to many problems today. We're just basically giving this introduction to you. So next time we'll come in with problems. So we're explaining concepts right now. Okay? So hopefully, and it may help to go through and read.
Weird concepts.
I understand. It's different. It's different. Unit vectors will be very important for us too. But if the length is 1, it's called what? Unit. In addition to that, the only way that we'll get the length of a vector to be 0 is if the vector itself is 0. Now, I must mention, 0 is a number, it's a constant, but we can also have 0 the vector.
You mean to put 2 F's in there?
Huh?
You mean to put 2 F's in there?
Yes, if and only if, I'm sorry.
Oh, okay.
If and only if. If and only if. Y'all know what that means?
Right.
You do? Okay.
Thank you.
If and only if means, okay, most times, this goes back to logic now. Most times if it just says if,
One way.
one way. If and only if, both ways. Logic. Okay. Now, the 0 vector in component form is just what? It's just 0, 0 in both spots. But the only way we can have the length of a vector being 0 is if the vector itself is 0. Is if the vector itself is 0.
Otherwise, it's going to be some kind of whole number.
Or fraction. Or radical.
You don't like fraction.
I know it. Or radical.
You going to put a fraction on this, or?
Sure I am.
Oh, you got to be kidding me.
Okay. Let's talk about equality for a minute. Two vectors, U1 And here now we're talking about component form. Or U, which is U1, U2, and V, which is V1, V2, are equal. If, and only if, U1 equals V1 and U2 equals V2. Now that makes sense, doesn't it? These two are equal if what? The first components are equal and the second components are equal. Does that make sense? There should be something that makes sense. Okay? They're equal if the first components are equivalent and the second components are equivalent. It has to happen for both. Has to happen for both. All right. All right, let's look at an example. And I think we may end it at this example today and pick up next time. Okay? Find the component form and magnitude of the directed line segment with initial point -2, 7 and terminal point 5, -17. Okay? Similar to what we did there. We want to find the component form and what? The magnitude. The initial point is our P1, P2, terminal Q1, Q2, right? So this vector in component form is what? Q1 minus what? P1 and what? Q2 minus P2, which is what? 7 and what? -24. And that's a component form now, right? That pushes that initial point where? To the origin. That's what it does. Now, they also asked us to find the magnitude of the length. So the magnitude of V is what? The square root of, because we're in what? Component form now, we can use this one, where it's the first component squared plus the second one squared, and overall we take what? A square root. Which, 25? Is that what you get? Oh, that's okay. It's 25. Okay? All right, y'all. Huh? No, it's not. It's just something new that you're going to have to become accustomed to doing. Okay? But I do think we need to stop it here before we get into another concept. Any questions about anything before we dismiss? Well, this will end our talk about law of cosines and our beginning talks on vectors in the plane.